You're falling, not through air. Not through space as you know it. You're falling through a gravitational field so powerful that it's stretching you like putty, elongating every molecule in your body at different speeds. Your feet, just a meter closer to the neutron star than your head, are being pulled with a force thousands of times stronger. The pain would be unimaginable, except you can't feel pain anymore, because the neurons that carry pain signals are being ripped apart atom by atom. Your bones, the hardest parts of your body, are snapping like dry twigs. You're becoming a human noodle, a process astrophysicists call spaghettification, and you have less than a millisecond of consciousness left before you cease to exist as anything resembling a human being. But let's back up. How did you get here? And more importantly, what exactly is this cosmic monster that's tearing you apart? A neutron star is what's left when a massive star dies. And when I say massive, I'm talking about stars that were 8 to 20 times the mass of our Sun. When these giants run out of fuel, they can no longer support their own weight, and they collapse. In less than a second, the core of the star, an area the size of Earth, compresses down to a sphere just 20 kilometers across. 20 kilometers, that's about the distance from downtown London to Heathrow Airport. The entire mass of something larger than our Sun crushed into a space smaller than a city. The collapse is so violent, so catastrophically sudden, that it triggers a supernova. The outer layers of the star are blown away at speeds of tens of thousands of kilometers per second. And what remains is a neutron star, an object so dense that a single teaspoon of its material would weigh about 1 billion tons. That's roughly the weight of Mount Everest, compressed into something you could fit in a spoon. The name neutron star comes from what happens during that collapse. The pressure becomes so extreme that protons and electrons are forced together to form neutrons. The star becomes, essentially, a giant atomic nucleus, held together not by chemistry, not by the normal rules that govern matter, but by neutron degeneracy, pressure, and gravity locked in an almost perfect balance. If you're fascinated by the extreme physics that govern objects like neutron stars, you'll find even deeper insights in our ebook, available in the description below. It explores the most mind-bending phenomena in modern astrophysics and cosmology, perfect for anyone who wants to understand the universe at its most extreme. Now, let's talk about what makes a neutron star one of the most hostile environments in the cosmos. First, there's the density. We've touched on this, but it's worth emphasizing. Normal matter has a lot of empty space. Atoms are mostly emptiness, with tiny nuclei surrounded by even tinier electrons orbiting at relatively vast distances. In a neutron star, that empty space is gone. Neutrons are packed together so tightly that the density reaches 500 trillion times the density of water. At that scale, physics starts to behave in ways that feel like science fiction. Second, there's the gravity. The surface gravity of a neutron star is approximately 200 billion times stronger than Earth's gravity. If you were somehow standing on the surface, which you absolutely could not do, you would weigh as much as a large mountain weighs here on Earth. A single misstep, a tiny stumble, and you'd slam into the surface with such force that you'd be flattened to a layer of atoms just a few nanometers thick. Third, the magnetic field. Neutron stars have the strongest magnetic fields in the universe, often trillions of times more powerful than any magnet we've ever created. Some neutron stars, called magnetars, have fields so strong they would be lethal from thousands of kilometers away. These magnetic fields can rip electrons from atoms and tear apart molecular bonds just by proximity. And fourth, the rotation. Many neutron stars spin fast, some rotate hundreds of times per second. These are called pulsars, and they emit beams of radiation from their magnetic poles like cosmic lighthouses. If you were caught in one of those beams, you'd be bombarded with lethal doses of X-rays and gamma rays. So when we ask what would happen to a human near a neutron star, we're not just talking about one danger. We're talking about a perfect storm of physics working together to annihilate you. Let's imagine you're approaching a neutron star in a spacecraft at 1 million kilometers away. Roughly 2.5 times the distance between Earth and the Moon, you might not feel anything unusual yet. Your instruments, however, would be screaming. Radiation detectors would be maxed out. The electromagnetic environment would be intense enough to interfere with electronics. If this neutron star is a pulsar and you're in the path of its beam, you're already absorbing radiation doses that would be fatal within hours. But you don't feel the gravity yet. Not really. Your spacecraft's engines could still overcome the pull, if you wanted to turn back. You won't, of course, because we're here to understand what happens when you get closer. At 100,000 kilometers, things start to change. The gravitational field is becoming noticeable. Objects in your spacecraft that aren't secured start to drift toward the neutron star's direction. You can feel a slight pull, a gentle tug that's growing stronger with each passing second. The tidal forces are beginning. Tidal forces are differences in gravitational pull across an object. On Earth, tidal forces from the Moon create ocean tides because the water on the side of Earth closest to the Moon is pulled slightly more than the water on the far side. Near a neutron star, these differences are catastrophic. Your body is about 2 meters tall. At this distance, the difference in gravitational force between your head and your feet is already measurable, already uncomfortable. You'd feel stretched, like you're on a medieval rack. It's not painful yet, but it's deeply unsettling. Your blood is starting to pool in the parts of your body closest to the neutron star, at 10,000 kilometers. You've crossed what physicists call the innermost stable circular orbit for a non-spinning neutron star. There's no turning back now, even if you wanted to. The escape velocity has exceeded what any reasonable propulsion system could achieve. You're locked in. The tidal forces are now severe. Your body is being stretched noticeably. The cells in your feet are experiencing acceleration forces, orders of magnitude stronger than those in your head. Your cardiovascular system is failing. Blood can't flow properly when different parts of your body are in essentially different gravitational environments. Your heart, evolved to pump blood in Earth's gentle 1G environment, is useless here. You'd lose consciousness within seconds from the combination of blood pooling, cellular disruption, and the sheer mechanical stress on your body. But unconsciousness would be a mercy, because what comes next is far worse. At 1,000 kilometers, your body is no longer holding together. The tidal gradient, the difference in gravitational acceleration from your head to your feet, is now so extreme that the molecular bonds holding your tissues together are being overcome. You're stretching, elongating, becoming thinner and longer. This is spaghettification. In earnest, your skeleton, your bones, the structural elements that define your shape are being pulled apart. The calcium phosphate crystals that give bones their strength are separating. Your spine is extending, vertebrae pulling apart. Your skull is deforming. The proteins that make up your muscles, your organs, your skin, they're all aligning in the direction of the gravitational field, all being drawn into long, thin strands. At the same time, you're being compressed from the sides. The gravity is pulling everything toward the neutron star, which means lateral compression. You're becoming narrower as you become longer, a human cylinder than a human thread. If somehow you still had functioning eyes and a functioning brain to process what they were seeing, you'd notice the neutron star's surface rushing toward you at an appreciable fraction of the speed of light. At these distances, with this much gravitational potential energy converting to kinetic energy, you're accelerating faster than anything you've ever experienced. At 100 kilometers, we're no longer talking about you as a person, or even as a collection of organs. We're talking about you as a stream of molecules being pulled inexorably downward. The gravitational gradient is now so steep that individual molecules are being torn apart. Complex organic molecules, the proteins and lipids and nucleic acids that once formed a living, thinking human being, are fragmenting. Chemical bonds are breaking not because of chemical reactions, but because of mechanical stress. The temperature is rising. As you fall deeper into the gravity well, gravitational potential energy converts to kinetic energy, and kinetic energy at the molecular level is heat. Your molecular fragments are heating up, glowing, emitting radiation. If the neutron star has a powerful magnetic field, and most do, that field is now interacting with any charged particles in your molecular stream. Electrons are being stripped away. What's left of you is becoming ionized plasma, a hot gas of charged particles spiraling along magnetic field lines. At 10 kilometers from the surface, you're traveling at a significant fraction of light speed. Time dilation effects from both your velocity and the intense gravitational field mean that if somehow an outside observer could watch your descent, they'd see you slowing down, your clock running slower than theirs, asymptotically approaching but never quite reaching the surface from their perspective. But from your reference frame, if consciousness were somehow possible, you'd hit the surface in milliseconds. The surface of a neutron star is not like any surface you know. It's not rock, it's not metal. It's a crystalline lattice of atomic nuclei, primarily iron, locked in place by gravity and pressure. The ground is harder than diamond, harder than anything we can create or even imagine. When your stream of atoms and ions hits that surface, it doesn't bounce, it doesn't splatter, it joins the surface. The kinetic energy of your impact is so enormous that you and the surface briefly achieve temperatures of billions of degrees. You create a tiny flash, a minuscule burst of X-rays and gamma rays, and then you're part of the neutron star. The atoms that were once you are now crushed, compressed, integrated into the neutron star's outer layers. At depths of just a few meters below the surface, the pressure is so extreme that atomic nuclei are crushed together. Deeper still, at depths of hundreds of meters, matter exists in a state we call nuclear pasta, where nuclei are squeezed into strange configurations that resemble sheets, tubes, and other shapes, named whimsically for their resemblance to lasagna, spaghetti, and gnocchi. Deeper still, in the core, we honestly don't know what happens. The pressures exceed anything we can recreate in laboratories. The densities exceed those of atomic nuclei. Matter might break down into a soup of quarks. There might be exotic states of matter we haven't even theorized yet. You, or what was once you, might become part of that mystery. Let's take a moment to understand the physics that destroyed you. Tidal forces arise because gravity gets stronger as you get closer to a massive object. The equation is simple. The gravitational force is proportional to mass divided by distance squared. Double the distance and the force drops to 1/4. Have the distance and the force quadruples. For a large object with weak gravity, like Earth, this difference across a human body is negligible. The difference in Earth's gravitational pull between your head and your feet is less than 1 part in a million. You don't notice it. For a small object with intense gravity like a neutron star, this difference is everything. The force at your feet might be thousands or millions of times stronger than at your head, even though they're only 2 meters apart. Your body experiences not just gravity, but a gravitational gradient, a change in gravity over distance. That gradient is what tears you apart. The technical term for this is the tidal acceleration, and for a neutron star, it's governed by the equation that includes the mass of the star and the cube of the distance. As you get closer, the tidal force doesn't just increase, it increases catastrophically fast, half the distance, and the tidal force increases by a factor of 8. This is why black holes and neutron stars are so lethal. It's not just that they have strong gravity. Lots of things have strong gravity. It's that they combine strong gravity with small size. That combination creates gradients steep enough to tear matter apart. Neutron stars aren't just cosmic killers, they're laboratories. Because conditions near them are so extreme, they allow us to test physics in regimes we could never achieve on Earth. When two neutron stars collide, they create gravitational waves, ripples in spacetime itself that we can now detect with observatories like LIGO. These collisions also forge heavy elements: gold, platinum, uranium. Most of the heaviest elements in the periodic table were created not in normal stellar fusion, but in the catastrophic collisions of neutron stars. The gold in your jewelry, if you're wearing any, was likely forged in a neutron star collision billions of years ago. Neutron stars also help us understand the fundamental nature of matter, what happens to matter at nuclear densities and beyond. How does the strong force behave under extreme pressure? These are questions that probe the deepest levels of physics, and neutron stars are the only natural laboratories where we can study these conditions. And there's a philosophical dimension too. Neutron stars represent matter at the edge of stability. Make them any denser, add any more mass, and they collapse into black holes. They're the universe's way of showing us the absolute limits of material existence, the boundary between matter and the void. You might be wondering why we should care about objects that would destroy us so thoroughly, objects we could never visit, could never touch, could never even approach without being annihilated. The answer is that neutron stars tell us about the universe at its most fundamental. They're time capsules from the deaths of massive stars. They're precision clocks, with some pulsars keeping time more accurately than atomic clocks. They're gravitational wave sources, allowing us to listen to the universe in an entirely new way. They're element forges, creating the building blocks of planets and life. Every neutron star in our galaxy is a monument to a stellar death, a compressed core that once powered a sun that may have had its own planets, its own story. They remind us that the universe operates on scales both larger and smaller than we can easily comprehend. Larger in the vast distances between stars, the enormous energies of supernova. Smaller in the quantum mechanical effects that govern neutron degeneracy, the nuclear physics that determines their structure. When we study neutron stars, we're studying the universe's most extreme environments. We're pushing our understanding of physics to its limits. We're asking questions about gravity, about matter, about the fundamental fabric of reality. You would never survive an encounter with a neutron star. From the moment you crossed into its gravitational dominion, your destruction would be inevitable, thorough, and complete. You'd be stretched, compressed, heated, ionized, and ultimately integrated into an object so dense, so extreme, that the atoms of your body would cease to exist in any recognizable form. But in understanding how a neutron star would destroy you, we've learned something profound. We've glimpsed the universe at its most extreme. We've seen matter pushed to its absolute limits. We've understood that the same physics that gently holds us to Earth's surface can, in a different configuration, tear matter apart, atom by atom. Neutron stars are not evil. They're not cruel. They simply exist, following the laws of physics to their logical, extreme conclusion. They're the universe, showing us what's possible, what happens when gravity and matter meet in their most intense confrontation. And in that confrontation, in that cosmic violence, there's a strange and terrible beauty. A reminder that we live in a universe far stranger and far more magnificent than our everyday experience suggests. A universe where dead stars become diamonds of nuclear matter, spinning hundreds of times per second, singing songs of gravitational waves and electromagnetic radiation across the cosmic dark. A universe where your destruction would be absolute, but our understanding, our quest to comprehend these cosmic monsters, continues to grow, pushing back against the darkness. One equation, one observation, one moment of insight at a time.